In this video, we'll try to analyze a DC circuit using Kirchhoff's voltage law and current law. So we have here a schematic diagram of a simple circuit with 2 voltage sources and 3 resistors. First thing we need to do to prepare ourselves for KVL equations is to identify the polarities of each of the resistors, as well as the batteries, of course. Okay. For the batteries, it's easy to identify the polarities of each, because basing on the schematic symbol, the side with a longer line is always positive, and the side of the battery with the shorter line is the negative terminal. So for V1, the positive terminal is up here and the negative down here. For V2, the same principle applies. So the longer line is up top, shorter line down at the bottom. For the resistors, on the other hand, it will depend on the voltage sources. So we'll have to do a little investigation as to which side of the resistor receives more pressure for the current to flow. So if it's on the left or on the right, from the top or the bottom. And the greater the pressure, the more positive the terminal will get. Okay, so let's look at R1. For R1, we have its left side connected directly to V1, while the right side will receive a pressure from V2, but then that pressure is diminished because of this resistor here. So by the time it reaches R1, it's not a pressure of 4 volts, it's less. So compared to the right side of R1, which is directly connected to a 5 volt battery source or voltage source, we expect that the pressure on the left side is greater. So we can assign the polarity of R1 with a plus sign on the left and a minus sign on the right. Using the same principle on R2, we expect that the positive terminal is on the right and the negative terminal is on the left. Now for R3, it's easy to see that both V1 and V2 will be applying pressure from the top. So R3 will have a positive polarity on the top and a negative polarity at the bottom. So at this point, we have assigned the polarities of the batteries and the resistors in our circuit. The next thing, before we proceed writing our equations for KVL, we need to look at the loops of the circuit. So the KVL prioritizes or focuses on the loops of a circuit. So I went ahead and wrote here loop 1 and loop 2, which corresponds to this loop and this loop respectively. Okay, so if I write here by KVL, we have the following equations. So at loop 1, the summation of the voltages is equal to 0. So as a recap, Kirchhoff's voltage law says that the sum of all the voltage sources and the voltage drop present in a closed loop must equal to 0. Okay. So in writing our equations, the polarities will play a major role. So you'll see, let me just use a guide. So say for example, I'll look at loop 1 in a clockwise direction. So I'll be looking at the elements from here going to the top and to the right. So all you have to do to know what sign will be as. So for us to write the KVL equations, we just have to look at which terminal are we gonna leave the element. Say for example at V1, I can write a positive 5 volt value for V1 because we left V1 at the positive side. For R1, we write minus 2 ohms times the current through R1, I'll just name it I1, and we use the minus sign because we left that resistor through the negative terminal. And for R3, the same thing. 1 ohm times the current through R3. I'll just write it I3. And this will be equal to 0. So let me just fix that very quickly. So summation of voltage. At loop 2, we have the following equation. So actually choosing whether you want to look at your loop or collect the terms using a clockwise or counterclockwise direction is entirely up to you. So I'll just go with using clockwise direction. So moving through R3, I have a positive value. It's 1 ohm times I3 plus 3 ohms times I2, or the current flowing through R2, and then I have minus 4 volts. So at this point I have all the equations for all the loops in this circuit. I'm done with the Kirchhoff's voltage law. Let's move on to the Kirchhoff's current law. So with the Kirchhoff's current law, or KCL, we are not considering the loops anymore. Instead, we're looking at nodes. So a node is a certain point on the circuit where you can see branching of elements happen, like these 2 points here. So I can just name them node A and node B. Okay. So the rule for KCL, now that we're dealing with currents, is that when the current is moving towards a node, we will consider it positive. When the current is moving away from the node, we consider it negative. So for us to know which direction the current is flowing through each resistor, we consult the polarities one more time. So for resistors, currents will be flowing from the positive terminal to the negative terminal of that element. So for this resistor, it's this. For this resistor, it's moving from top to bottom. Okay. So if you're unsure, if at the future some certain problem, you're unsure if your current direction is correct, don't worry. For as long as your polarities and the direction of your current agree, that is, moving from positive to the negative side of the resistor, even if it has been assumed improperly on the wrong direction, the magnitude of your current will still be correct. The only thing that will be wrong is the direction that is represented by a negative sign. So if after computing you find that your current is negative, don't worry, you just have to flip the direction of the current and it will be positive. It will be correct. Let's continue. So at node A, we'll have the following equation. The summation of current is equal to 0, and the currents involved at node A are I1, which is positive, I2, which is also positive, because both of them are moving towards A, and then I3, which is negative. Node B, you also have 3 currents. You have I3, which is moving towards it, and 2 currents here. Now, this current here is also I2, and this current here is also I1, because if you look carefully, this branch here, we have elements in series, connected in series, and elements connected in series have the same current. So the current here is I2. Similarly, on this side, you have I1 as your current, because R1 and the battery V1 are connected in series. They have the same current. I3 will have a different current because the currents I1 and I2 will combine at node A and will split at node B. So you can see that these two equations mirror each other, essentially because the currents involved on both nodes are the same currents, but they are just behaving in a different or in an opposite manner. In node A, I1 and I2 are moving towards a node. In node B, I1 and I2 are moving away. So that's fine, that's perfectly fine. So we have now all the equations we need to solve the problem. Now in mathematics, if you can remember, the number of unknowns would require the same number of equations to solve for the unknowns. So in this circuit, we have 3 unknowns, I1, I2, and I3. So we only need at least 3 equations for us to be able to answer this problem. And we have 4, so that's more than enough. Now, aside from the number, it is also required that our equations are independent of each other. So how do we know if one equation is independent or dependent with another equation? We say 2 equations are independent. Let's take, say, equation 1 here and equation 2 here. We say these 2 equations are independent if there is no constant that if we multiply at each of the terms of the equation would result to the other equation. So equation 1 and equation 2 are independent. But if you look at equation 3 and equation 4, these 2 equations are dependent, because if you multiply -1 to each of the terms in equation 3, you'd actually get equation 4. So the 3 equations that we're going to use to solve this set of unknowns would either be equation 1, 2, and 3, or equation 1, 2, and 4. It's up to you. So I'll just go with using equations 1, 2, and 3. Now I find it easy to use matrices to solve for these unknowns. After all, we have a system of linear equations. So we just have to write each of these equations in the following format. So let's take, say, equation 1. We have 5 volts minus 2I1 minus 1I3 equal to 0. So if we're going to rewrite this equation for us to be able to put it into the matrix, we just have to transfer all the constants to the right side of the equation. So you have -2I1 plus 0I2 minus 1I3 equal to -5. So you have your -2, 0, and -1 equal to -5. You'll do the same thing with equation 2 and equation 3. Equation 2, we have 0I1, positive 3I2, and positive 1I3, and that's equal to 4. And then finally, equation 3, you have positive I1, positive I2, -1I3, and 0. So we have now our matrix, so we can use a calculator, or you can solve it manually if you want. So we finally have the following values for our current. Right. I1 is equal to 1.45 repeating amperes. I2 is equal to 0.63 repeating amperes. And I3 is equal to 2.09 amperes. So you can see that all of our currents are positive, which means that the assumption for the current directions are all correct.